Hello students, welcome to the module on trigonometry. In this video, we'll discuss the wrapping function at multiples of pi over 6. Let's consider the wrapping function at pi over 6. So we will draw the unit circle, my x-axis, my y-axis. Here's my point 1, 0. And my wrapping function is found by drawing the tangent line to the circle at 1, 1, and calling this the theta axis. And I will go up pi over 6 units on my theta axis and wrap that around the unit circle. And the value I end at is my point xy, which is omega of pi over 6. So, to figure out what this value is, we note that pi over 6 is some multiple of 2 pi. And this will tell me that k is equal to pi over 6 times 2 pi, or 1 over 12. So I have to draw 12 portions, equal portions of the unit circle. So I'll have 3 in each quadrant. 1, 2, 3. Each of those are my 3 portions, another 3 in this quadrant, and so on. So I've drawn a total of 6 portions of the top half. There are also 6 portions of the bottom half. So this triangle over here, this right triangle, is the triangle I'll need to consider. So what we'll do is we'll look at this long triangle over here and connect the dots. And so let's see what happens. Let's look at this long triangle. We know that this angle over here is my pi over 6, and this angle over here is also equal to pi over 6. And so that tells me the angle in between here, so I have pi over 6 and pi over 6, so if I add those two together, I get 2 pi over 6. So this angle over here is going to have to be 2 pi over 3. So if I cut this in half and make a right triangle over here, what will this tell me? This and this are parallel, where this is my x-axis, and this is the line I've drawn. So that tells me that this angle over here must be pi over 6. And this angle over here, if that's pi over 6, this has to be pi over 3, and this has to be pi over 3. Now, this is a 1 length, and this is a 1 length because they are both radii of the unit circle. So I can find out what this length is by using the Pythagorean theorem. So we'll do that. So I will have a 1 over here, 1 over here, and so this is an isosceles triangle, which tells me that this is pi over 6. And so now we have the exact same thing as a triangle from the wrapping function of pi over 3 case. So the rules are simply reversed. So we know that the wrapping function of pi over 3 was found by going over here, and that told me that the x was 1/2 and the y was root 3 over 2. And so now I have the same exact triangle, except now the angles are flipped. So by using the symmetry of this triangle, the wrapping function of pi over 6 will be this length over here. This x length will correspond to the root 3 over 2, and the y length will correspond to 1/2. Now the other values of pi over 6 that occur in different quadrants, so for example, if I look at the wrapping function of 5 pi over 6, which will occur in the second quadrant, that's when the x is negative and the y is positive. So by illustration, this will be negative root 3 over 2, 1/2. Over here in the third quadrant, we'll have the value, the wrapping function of 7 pi over 6. Both will be negative. Negative root 3 over 2, negative 1/2. And the wrapping function of 11 pi over 6, which will lie in the fourth quadrant, will have the x being positive and the y being negative. So using the symmetry relationship between the wrapping function at pi over 3 and pi over 6, we see that once you know the wrapping function of the pi over 3's, you simply just interchange the entries of x and y to find the wrapping function of the multiples of pi over 6. So together with the multiples of pi over 4, we have the multiples of pi over 4, pi over 3, and pi over 6, and those are the standard values we'll use when computing trigonometric functions. Thank you very much.